I wonder if you could provide further detail about the experimental setup that you and Chiara have been working on, and what are the predictions of the outcomes given the constructor theoretic principles that you've been applying to these systems of gravity and quantum mechanical systems interacting.
Yes, and I think it's nice to continue actually in this spirit of information theory, because I think certain things become very simple and transparent if you think about it in this way. So what Chiara and I really thought is, we thought let's have two quantum systems, if you like, or if you like to think of it in terms of constructor theory. They need to be quantum-like. They actually don't even need to be strictly fully quantum. They only need to have some quantum properties. And the key one here is this non-copyability. So you have to have two sets of properties in each of these systems that individually can be copied, but when you put them together, they cannot be copied. It's enough to have two of these. You don't have to apply that to all properties of your system. So they are kind of not even fully quantum, if you see what I mean. You take a little bit of quantumness and that's enough for this experiment. So now the question is, you take these two systems which have this non-copyability property, and you realize that at the end of your experiment, they can actually become fully quantum entangled. So that means you can actually make measurements on each of these systems and show that their correlations are the same as the ones we observe in Bell's inequalities in quantum mechanics. So they are maximally correlated. It's something that classical physics, if you like, cannot achieve. And then what Chiara and I have been thinking is, what kind of medium between these two systems, what kind of properties does the medium need to have in order to be able to mediate this kind of entanglement between these two quantum-like systems. So if these two systems can, at the end of your experiment, become entangled, the channel between them, what kind of properties does this channel need to have? And the beauty, so this channel could be anything. And of course, the most exciting, as you have been asking as well, here is gravity. What happens if this channel really is the gravitational field between these two systems? And the interesting thing is that if all the states of this system in between are perfectly copyable, which means if it's really classical-like, then you will never be able to entangle these two quantum systems at the end of your experiment. So this is a very nice result, because it allows you to rule out all sorts of hybrid-like theories, which say it's okay to have some systems in your universe being quantum, if you like, and it's perfectly okay for the rest of these systems to be classical. What we are saying is that if these other systems are used to mediate the interaction between quantum systems, then actually they need to be quantum themselves, at least to the same degree as the quantum systems that you are testing. And this is very interesting, because the whole idea really is lifted to this set of information theoretic principles, and you don't need the full machinery of quantum physics or classical physics, Hamiltonian dynamics. All of that is unnecessary for this logic.
So constructor theory has allowed you to predict that if quantum systems become entangled through any medium, including gravity, then that medium must be non-classical.
That's it. It must be non-classical, and you can say non-classical to exactly the same degree as the entanglement that you created.
Okay, so that's a nice prediction from constructor theory. I think we should, by the way, let's define what exactly you mean by classical.
Good question here, because again, people really disagree on these notions. It's very unclear in many ways. Certainly, if you take the strictest definition, then you would be talking about Newtonian mechanics. You know, that's kind of the first proper physical theory. And you can talk about it as certainly underpinning. So now, you know, you distill the logic from that, and you can say, well, the same logic underpins also electrodynamics, if you like. So Maxwell's theory is all classical as well. And then any other field theory that follows from that, certainly general relativity, you could think of also as classical, because in a way it obeys the same logical principles. But what you have to be careful about is that the fundamental entities in these theories are not necessarily the same, even though we call them all classical. So what I want to say is that for Newton, everything is really made up of particles. You're talking about particles, their locations, their speeds, and once you have that information, you use Newton's laws of motion to calculate all the future states. With Maxwell, it's different, because Maxwell would say, in my theory, the fundamental entities are waves. So you see, even though we would still call Maxwell's theory classical, already certain notions like superposition of waves are possible in these wave theories. And that almost starts to sound quantum mechanical, but we wouldn't call it quantum. And the reason why we wouldn't call it quantum is because of this copyability, that actually all states of Maxwell's fields can in principle be fully copied, unlike quantum states in general. So I would say the most general definition of classicality is really any theory that's not quantum, if you see what I mean. So that includes all the wave theories of classical physics, all the particle theories of classical physics, and they are classical simply because every state that you give me can in fact in principle be copied, it can be cloned. And now, you know, quantum theory violates this immediately. And then you can also ask, so what is quantum? And I would say anything that has this kind of property that you can build on, you could consider quantum-like in some sense.
So if the outcome of the experiment that you and Chiara have been working on, if it shows that in fact the quantum systems have become entangled via gravity, then that means that gravity must have quantum properties, or any post-gravity, post-quantum theory must be such that gravity has, let's say, non-copyable states. Is that right?
Yes. Yes, you're absolutely right. That means that gravity must have non-copyable states. And of course, the only really theory that we know currently with this property is quantum mechanics. So, you know, you would immediately be thinking it's got to be quantum at least to some degree. And I think this is very interesting because, like I said, copyability comes in, you know, that you cannot copy all of the states of your system. And the only other assumption, and we discussed it already, is locality. And actually with gravity, we know already the classical gravity should be local. Certainly general relativity is a local theory. So that means, you know, when the quantum system couples to gravity in one position, then that's the only place where things can change. And then this change can gradually travel, but it cannot travel faster than the speed of light to other locations. So somehow copyability and locality give you everything you need really to conclude that gravity must be quantum as well in this case.
So let's say your experiment is successful in showing that, in fact, gravity must be non-classical in some way. And we talked about this a little bit at the very beginning, but which of the candidates for post-quantum, post-general relativity theories would immediately be ruled out?
Yes, I think immediately any theory that suggests that you would get some kind of a collapse of quantum superpositions would be ruled out, because of course, unless your theory predicts that the collapse takes a very, very long time. So if the time that it takes to collapse is longer than the experiment which you perform, then these theories could still survive. But of course, they could be unrealistic for many other reasons, these kind of theories. So anything that says gravity will actually remain classical, and it will even force quantum superpositions to ultimately become classical. This certainly cannot explain entanglement between two quantum systems. So there are various theories there. There are various, I already mentioned corrections to the Schrödinger equation that are meant to induce collapse due to gravitational interaction. There are theories that go under the name of quantum field theory in curved space-time. So what these theories do is they take quantum field theory, but instead of applying it to all the degrees of freedom of gravity, they're thinking of gravity being the background, classical background to these fields. So they are what I would call semi-classical theories, in the sense that matter is quantum, but gravity is still treated in a classical way. These theories are automatically ruled out as well if you get entanglement in this experiment. So many of these alternative approaches, I think, would be invalidated in this case.
That would be very productive unto itself.
I think so. I think you're right, because as you know, science is all about ruling things out, really.
Yes.
Yeah.
So what about things like string theory and or loop quantum gravity? Because these are very popular, I think, in the collective consciousness.
Yes, I think both at this very low level, Newtonian level of approximation, should agree with our predictions. Because what we really all we need to make this prediction is literally we don't really need general relativity. We really just need general relativity in the limit of very, very weak gravitational field. And I think both string theory and loop quantum gravity, and in fact any what people would call canonical approach, to canonical just meaning let's quantize it the way we quantized other things. All of these approaches should actually survive this experiment. But like I said, the bad news there's always a bad news in science. The bad news is that you wouldn't be able to discriminate between them. That's what I think.
Now, let's say your experiment is unsuccessful in showing entanglement between
Yes.
quantum systems via gravity. Would you then say that there's something wrong with constructor theory, or maybe just the constructor theory of information? Or in what sense would you regard the outcome as problematic for constructor theory?
Yes, it's actually okay. There should be like a small warning there before we go in that direction, because of course we should assume that it failed. It failed not because we couldn't really control these massive superpositions, not because there are some other noises and effects, but I think you are asking if it really fails, and yet we are confident that nothing else was present there. Because I think my experimental colleagues are really all worried about the difficulty of the experiment. You know, they're saying you are asking us to superpose an object that's comparable in weight to a biological cell. It's a few orders of magnitude lighter than a biological cell. So it's really large for atomic physics. It's many orders of magnitude larger than an atom, a simple atom. In that case, in that sense, it's technologically extremely difficult because there are all sorts of other interactions that you have to control and so on. But let's imagine all of this is under control. We do the experiment and there is no entanglement. I think this really would suggest to me that there is something that we radically do not understand about quantum mechanics. You are right that this would force us to revise all of our basic assumptions. And the question, I think, in a way, I'm almost now, as we speak, even more excited about this possibility, because to us this would signal some really deep fundamental failure of something very big. So, and I would say that most people, in fact, would probably bet now that the experiment would be successful and there would be entanglement, which is why I'm saying that the other alternative would actually be much more surprising. And I think then you would start to question certainly what you mentioned, things like locality. You know, is the world really local? Could it be that there is something non-local in these kind of interactions? Could it be that this copyability or non-copyability property cannot apply to this situation? And I think this will be fascinating. And we wouldn't know, I would say, where to begin with this. You know, it would be a very worrying state of affairs. A bit like, you know, before relativity and quantum physics, when people couldn't explain Michelson-Morley experiment, black body, all of that stuff. And everyone was desperate to see which postulates should now be abandoned, actually. What can we preserve and what should we give up? And it's not clear at all.
Yeah, that would certainly be exciting if your experiment failed.
I think
I
so.
guess either way, it's very cool.
Yes, I think so.
So you had mentioned that you're collaborating with experimentalists. What do they tell you, or what do you know are the greatest impediments that need to be overcome in order to realize your experiment in practice?
Yes, I think the greatest really impediment is the fact that you really want to make sure that it's only the gravitational interaction that entangles the two systems. And even if you, so of course the strong force there, if you like, the strongest in that domain that's relevant is electromagnetism. So what you really want is you want your two systems to be neutral. You don't want them to couple electrically or magnetically in any way. And I think that's possible to find, but the problem is, as you will find, and of course, this underpins the stability of all solid state objects around us. So in a way, it's a good thing for our universe and for ourselves, but it's a bad thing for this experiment. The problem is that as soon as two neutral objects get close enough, they will induce electromagnetic interaction. This is known under various names, van der Waals force, for instance. And in fact, what leads to a bonding that when you scale it up gives you a typical solid, now for us would be a problem, because in our experiment, we want the two masses to be close because gravity is a very weak force. And so we want them to be so close that gravity becomes strong enough. But we don't want them to be too close for electromagnetic interactions to turn on. And I think finding this sweet spot where gravity is strong enough, but electromagnetism is not too strong, is the most important challenge here. And I think people give you various estimates. I've heard something like 100 microns. So between a micron, a millionth of a meter, and maybe 10 or 100 times bigger than that, people say this is roughly your regime where gravity could still dominate electromagnetic interactions. Because you see, if you end up getting entanglement, but you can't tell whether it's electric forces that generated this or gravitational, then you have a big problem there. You didn't really prove much. And of course, you know, I mean, humans are very used to these kind of problems, especially in science and engineering. So it's not impossible that people even engineer some kind of shield that you can put between these two objects, some kind of Faraday's cage, which would prevent electromagnetic interactions and still allow gravity and so on. So there are various ideas out there how to overcome this difficulty, but I think this is the main difficulty.
Now, this approach that you take, whereby you take one system that obeys quantum mechanical dynamical laws, one system that obeys the dynamical laws of general relativity, namely gravity, you put them together, you take the principles of constructor theory seriously to predict how the combined system will behave, and that leads you to a particular experimental setup in order to test that prediction. Despite the difficulties that you just outlined, is that still easier than directly testing, let's say, string theory or these other post-quantum, post-relativity theories that are out there?
I think so. I think it's much easier to test it like this, because the idea, I mean, the dream case scenario for an experimentalist is really just to derive one parameter. You know, you want your experiment to simply depend on a single parameter, and you want to give the regime the values of this parameter above or below which your theory succeeds or fails. So ideally for an experimentalist, they want to say, tell me exactly what to measure. And if the number is bigger than 1, then basically you falsify something. And that's the strength of constructor theory, because you rely on very, very few assumptions rather than having to to control many different things and bring in many assumptions. Here you are really talking about just a single number, which is the strength of the correlation between these two. And that's why I think this approach is very powerful. You don't need the rest of the machinery at all. You know, if you go into the details of string theory or loop quantum gravity, there are many, many additional assumptions. And of course, you can test them separately in principle, but I think they're very, very hard to do in practice.
And at the risk of predicting the growth of knowledge, as it were, do you have an idea of what a timeline looks like for this experiment?
Yes, I think I'm very optimistic about this experiment. I would say that we will see something very important already within the next 5 years. So it seems to me, if you really project the current rate at which people are controlling more and more macroscopic systems quantum mechanically, and this goes together with the technological industrial development of quantum computers that themselves are getting more and more macroscopic. It seems to me that if it continues at this rate, if nothing major really prevents it, I think within 5 years we will have an answer. And this really sounds exciting to me because, as we said, the answer could be surprising and we might have to think very hard beyond that, what to do next.
Yeah, it sounds like either way the experiment goes will be extremely exciting. You know, if the experiment is successful in showing entanglement between quantum systems, you get to rule out whole classes of candidate post-quantum, post-relativity theories. And if it fails, then physicists have to completely reconsider what's going on in the world.
I think so.
So what are you working on now regarding constructor theory and maybe experimentally testing it, or more on the theory side? Are you working on anything in that domain?
Yes, I think what's exciting to me at the moment is really to apply this logic to just to field theory in general, to quantum field theory in general. For instance, we have this principle of locality that I mentioned. That's very interesting. And the question is really, what does it mean? What is it telling us about nature? How should one really even encode mathematically this principle of locality? And I think if you look at quantum field theory, you've got two types. First of all, there is this mystery about the fact that we have two types of fundamental particles, bosonic and fermionic. You know, why does nature give us this? That's really by no means clear. And it would be nice if there was a deeper principle that really tells us about this. Certainly locality, in all of the proofs that we have, locality features extremely strongly in all of them. So there could be something that we learn by pushing that direction. Fermionic particles, in some sense, look more non-local, at least mathematically speaking. And yet we know that they're fully local according to all our experiments so far. So to me, it seems that this is an interesting direction also to push, both theoretically and to try to come up with some experiments that would test some of these basic ideas. So I think what's exciting to me is that by reapplying some of these principles, it seems that we can revisit some very, very fundamental notions. And actually, we can even test them with current technologies. So you can see this beautiful theory and experiment that work very close to each other in the lab. And it's within our reach now.
Yeah, that reminds me of something that I think is interesting, which is that I think in the sort of traditional conception of how physics works, people think that the deeper a theory goes, the more difficult it is to test experimentally, as we've kind of touched on. But with constructor theory, because you're appealing to principles rather than just talking about things in terms of smaller particles and so forth, it's not necessarily more difficult to test new ideas.
Yes, I agree with you that I think somehow this really is to do with our creativity and ingenuity. But I think even at this level of technology, there are many things that we are not necessarily aware of, we're not thinking about. And that's precisely, as you say, because we follow a certain approach rather than a certain other approach. So how we think about science and physics in particular is very important, what kind of interpretations we have, because that they lead us to ask different questions, actually. And I think what you're saying is very true, that even at this level of difficulty, there are many fundamental issues to investigate.
Yes, well, it's all very exciting. So Vlatko, thank you very much for your time. It's been fun.
Thanks a lot. I've enjoyed it very much myself.
Okay, great. Bye.
Bye.